Hello again, we're in episode 4 of our arcade development. This time we're going to get some colour patterns on the TV screen. I'll be showing you how it's done on the breadboard by hooking up the RGB signals and composite sync, and then we'll be doing the same in our Verilog code on the MiSTer. Let's get into it. Here's our circuit from last time. I've added a few things to get some patterns going. The first thing we need to add is the VBLANK circuit. That is the time in the vertical picture tracing that we don't want to allow anything to be shown on the screen. It's creating a black top and bottom border effectively. From the schematic we can see that the VBLANK is created using the now familiar 74LS74, the D flip-flop. It takes the NAND or NOT AND of the 128V, 64V and 32V as an input, and it uses the 16V as the input clock. The output is in the NOT Q output of the flip-flop, or in fact the Q output, depending on if you need it positive or negative. As we'll see in later videos, memory chips typically need a low signal to select them, so our schematic is using the low output. For our example, we're going to stick with the high output, which I'll explain a bit more when we look at the traces. So here I've added the logic analyzer to the VBLANK circuitry. We have the probes on the 128V, 64V and 32V, and the eventual input D to the flip-flop. We have a probe on the 16V clock signal, and then also a probe on the Q and not Q outputs. Let's have a look and see what traces we get from the logic analyzer. Sampling our 7 channels, we get nice clean data coming in. We've got channel 0, 1 and 2 to be the 128V, 64V and 32V. You can see that the frequencies of those waves doubling as you'd expect. Channel 3 is the result of ANDing those 3 channels and then reversing the result, creating a NAND D input to the flip-flop. You can see a bit better zoomed in. Channel 4 is the 16V clock input to the flip-flop, so we'll cause the channel 5 Q output to be the same as the D input on the next positive clock rising edge. Channel 6 is the not Q output, so the opposite. Nothing complex here, just pretty much as we'd expect. Now let's remember I'm recreating the actual arcade system board here, so we need to use a regular CRT display. To get a picture on my CRT, I need to add the red, green and blue outputs through a connector, and I'm using a VGA port to carry the RGB signal and the C-Sync. My PVM monitor expects the C-Sync to be on the H-Sync pin, and the V-Sync pin is not actually being used. I've included a view of the pinout that's shown on the wire side, or the side that goes into my breadboard. You can see from the schematic that each color signal comes from a chip through a 220 ohm resistor and connects to the monitor. We won't get into how this chip, which is actually a programmable color chip or PROM chip, is working in this episode. We'll cover that next time. For now, all we need to know is that we need to trigger the red, green and blue at a set time and when we're not in the H-blank or V-blank time period. To create a nice multicolored pattern, we need to AND the triggers with the H-blank and V-blank signals. I'm creating a pattern based on a specific HV timing output that we looked at in the previous episode. The best way would be to use a 4-input AND gate to AND the H timer, V timer, H blank and V blank, so 4 inputs, and have that as the color output. Unfortunately, I only had the parts making up this board, so had to get a bit creative using a 3-input NAND, reversing the polarity of that with a NOT gate, and then ANDing that output with the 4th trace. It's the same as a 4-put AND gate, but it's just a bit more work. So on my breadboard, as per the schematic, you'll see I've added 2 3-input NAND gate chips. We need 2 chips because we can't do it with 1. We have the inverter or NOT gate up there, then the last AND gate here, so then those go to the VGA port. As per the schematics, you'll see we're taking our H and V signals from the 161 counter chips we looked at last time. In actual fact, the NOT 256H on pin 11 of 6C is actually our H blank signal. So first, blue. We're creating that with the H32 and V32 signals, in addition to the H blank and V blanks as we just discussed. We also need the C-Sync signal for the TV to understand the incoming signal. The intended result should be 4 blue squares horizontally of 32 by 32 pixel size, and there are 3.5 of these vertically with the screen resolution of 256 pixels wide by 224 pixels tall. The size of the square is just how the input signal, in this case 32, compares to the pixel clock. Our pixel clock is equivalent to the H1 signal, so that makes sense that the H2 creates a 32 pixel box. Next, red is created using H16 and V16 signals and H and V blanks. We'd expect these to give us a 16 pixel by 16 pixel red box. We'll have 8 of those horizontally by 7 of them vertically. The spacing is equal to the color box size. Finally, green is created using the H8 and V8 signals. We'd naturally expect to get 8 pixel by 8 pixel boxes in green for these, and we'd have 16 horizontally and 14 vertically with our screen resolution. One thing to note is that typically our tile graphics are going to be 8x8 size blocks, since memory chips love to hold 8-bit sizes of data. We'll see more about this going forward in the series, but there's definitely a nice order to the whole system of multiples of 8. So we'll be showing all of these red, green and blue signals at the same time, whenever we're not in our H blank or V blank timings. In order to understand our final picture, let's add the blue and red together first. Here you can see the red and blue boxes where they don't overlap and where they do. The red and blue together make magenta. Next, adding in the green, and we have green color in the previous gap, and where green and blue meet we have cyan. Where green and red meet we now have yellow, and where all 3 green, red and blue meet we have white. So hopefully it's easy to understand how we've come up with a nice pattern with multiple colors on the screen. After connecting the chips up as described, here's the result on the PVM. It's exactly as we'd expect it, and a nice clear picture. It feels really great to think we've made a nice 8-bit type display in color with really only a handful of components. Now time to create the pattern without any components at all, in fact with only some additional lines of code. Okay, so I've got 3 files here open in Programmer's Notepad. Blink 1 was from the first episode where we got an LED blinking on the MiSTer. Tank B was the model sim code we got working in the last episode, and here is the code for this episode where we're going to get some patterns showing on the MiSTer. The bit we need from Blink is really only the top module part here where we have inputs and outputs. So remember we had a clock, FPGA clock 150, and LED power. So that was input and output. All of this stuff we're not going to use. We're going to use all of the code from the Tank B model sim. So we're just going to take most of that. We're going to take all the wires. We're going to take all the instantiated chips. Remember, we had our horizontal timer and our vertical timer. And what we won't be taking is we won't be taking any of the stuff related just to the simulation. So remember, I said before, we have to simulate a clock when we do model sim, and we have to simulate some changing of some of these parameters. So we're not going to carry those through. So if we just look at the Tank B FPGA for a minute, what have we got? So we've got our clock that we recognize. We've got our button, reset button. That is possibly a new one, but that's one of the buttons on the I/O board, and we can press that. Then we have the VGA outputs. In this case, we're not using VGA; they just happen to be called VGA, but they are RGB S effectively, so RGB and sync. So we've got VGA HS, so horizontal sync, VGA VS, vertical sync, and then we've got the outputs, which are 6 deep, 6 bits of red, green, and blue, and all of these will be they will be assigned in the Quartus 2 software when we assign the pins, which we'll see in a minute how we can load that in. We are then just doing all of the definitions of the wires here, and then we've got our PLL that we recognized before. We put in a PLL in that first episode where we got here. The only thing I've done over here is I have added the reset. So we've got a reset, and the reset is connected to that reset is connected to the reset button. So when we press a button on the outside world, it connects to that reset, which then also resets the PLL. And the reset is used and will be used in the circuit as we build it up as well. So we've got the same horizontal timer, we've got the same vertical timer, that's exactly the same code, but we're adding a few things. So we talked before about the VBLANK circuit. So obviously we have to add that in. We're going to add that in exactly like we added it in on the breadboard. In that flip-flop for the in that chip IC-F5, you'll remember we did actually have 2 flip-flops. The one that was creating the VBLANK, which was number 1, and number 2, which was creating an IRQ, which we'll get onto later on in the video series. Don't worry too much about number 2, it is filled in here. But effectively, what do we have as inputs into the first flip-flop? We have this F51D. That, as I said before, is just a naming convention, and we've defined it up here. As we saw earlier, it is the V128 with the V64 and the V32 all ANDed, and in fact NANDed, because we make it negative there, or exactly the opposite of what it would be. And that is then fed into D, exactly as it should be as per the schematics. And then the output we have in Q1 and not Q1. I should say the clock first is V16 as we've seen, so we're setting it here exactly the same, V16. And then the output is VBLANK, exactly as the schematics. Now, earlier on I suggested that the schematics are not Q1, and that was about the fact that we're gonna use this VBLANK with a chip that expects a low 0 to be the thing that chip selects, so it turns on the chip. In this case, we're not doing that. We're just creating an output to VGA, so we actually want it to be the opposite. So just temporarily for this episode, we're going to have VBLANK being a positive when it's most of the time, and when it's not VBLANK, or at least the blank part of V is low, and otherwise it's high. we make that the opposite way when we start using chips, as we're going to see in future episodes. So we've put in VBLANK, that's fine. What else have we put in? Well, we've put in a couple of things. The same wires as we looked at on the breadboard, whereas we needed a few chips on the breadboard to create our red, green and blue. It's far easier here. It's literally just one statement in code. So H16 and V16 and our H blank and our V blank, when they're all true, then wire red equals true. So wire red is going to be 1. Same with green, except green obviously remember is H8 and V8 and the H blank and V blank, and blue is H32 and V32 with a V blank and H blank. Then we take those reds, that's one single bit, and we need to make it a 6-bit wide entity for the VGA, because we've got a good color depth on MiSTer, which means you can get lots of different colors. That color depth is 6 bits wide. So to create that 6 bits wide color depth, we concatenate that one red bit 6 times, and that's what these curly brackets do. We create basically 6 bits out of that one. So this is the outside world VGA tag, VGA-R, VGA-G, VGA-B, and the VGA-HS, which is the horizontal sync if you were doing VGA, is actually the composite sync that we've created previously in our simulation. It's the same composite sync. All of those 4 there are going to see the outside world with being a proper output that's connected to a pin of our FPGA. So that's the code, really simple, and we'll see next how to what we'll do in Quartus 2 to get it running. Okay, so one easy way to create pin assignments for the whole of the MiSTer I/O. Last time we did it manually by typing out which pin it would be. That will obviously take a long time to do all of the pins, so the best way is to get a previous project that's been done and export the pin assignments. So if we open a project that we've downloaded from the GitHub, here we've got arcade.oricon MiSTer main, that's downloaded from the GitHub. Open our project there, wait for it to open. Okay, so we've got that open now. Now all we need to do is go to our export assignments, in assignments, export assignments, and then we say OK. And then what that has done is it's created a file. Here we're in that there we've got atom net lists, and in there we've got this file here, arcade.oricon, and if we open that up, you'll see that has all of the pin assignments all the way through. So what we can do there is we can copy and we can paste that into our folder there. We can even rename it to be MiSTer pins.qsf, and we can import that later on into our project. Okay, so I'm in my Quartus 2 software here, and we're going to go into load the project. Now you can get this off the GitHub for episode 4, Tank B FPGA I've called it. And what we're going to be doing is we'll add to this every single time. We'll add a bit more code to it, and it'll just be in the GitHub as the next episode. So then we won't need to keep going through setting up the code every single time. So so I've already loaded it previously. I haven't compiled it. It'll be an uncompiled version actually on the GitHub because it creates a bunch more files. So it's as small as it can possibly be. What we can do is we can compile it. Let's compile it once. It says we've already compiled it, but just for interest we'll do that again. I'll probably speed this process up in the video, so we don't need to sit here watching it slow speed. Okay, so we're done there. One thing I did want to show was importing pin assignments. We've talked previously about pin assignments, so we've exported pin assignments from another project. To import the pin assignments, we just say import and we go and find them, and in this case it would be master pins, and I would say OK, and then say OK there. MiSTer pins, sorry, not master pins. We'd import MiSTer pins, and there we go. Now if you've never imported assignments before, you would have to compile, import them, and then compile again, because you can't assign them to a non-compiled design. Okay, so now we can program the device. We go down to programmer, and then we need to set up again the auto detect. For some reason it lost it. Kill that one. It's just all of the same process that I did last time. Go over that video if you don't remember. So that's fine now. And then if we press start, and we've got our nice colorful pattern on the screen, so it's exactly what we want. Perfect. Okay, so one thing I did want to show you extra is I want to show you doing a bit of troubleshooting with a piece of this software called SignalTap II, which is a part of this software that you use for the MiSTer. And so ModelSim that we used previously was simulation software, and it's very good for troubleshooting your code. Typically what you would do is work out how your code is working in a simulator first, like ModelSim. When you're happy with it, you can port it over to an FPGA, like the MiSTer. But typically something might go wrong when you do that porting it over. And it might be something silly like I had the reset ran the wrong way. You want to be able to do some troubleshooting with various different pins and wires in your code, but on the MiSTer. And so SignalTap II is a great way of doing that, and we're going to show you that next. Okay, so to get SignalTap going, let's go to Tools, SignalTap II Logic Analyzer. And what have we got over here? So we've got the first bit here. This is our basically our connection between our computer and the MiSTer, and it needs a file to go in there. But this is like our programmer dialog box that we had before. It's just squished into this little area here. This stuff up here is wanting you to do some programming or some compiling. So that's how we get interrogating. This bit down here is where we set the clock, because we need a reference clock. This thing is basically like the logic analyzer that we had before, but we need to give it a reference clock to do the timing. And that can be your 50 megahertz clock of the MiSTer if you want, or if you're looking for something a little slower, then you can use a different slower waveform. And you have a particular sample depth. So let's say you have here, you can have 512 bytes, you can have 1K, 2K, 4K. The good thing with the MiSTer is it's a very big FPGA. So this is actually taking space on the FPGA. So when you use lower cost FPGAs, you don't really have a lot of chance to then interrogate your system on SignalTap II in the FPGA, because this is effectively capturing a lot of data in the FPGA itself. That's how it can be so fast. But it does take up memory. So typically what you try and do is go for something that's not too big, but also is not an over-the-top clock frequency that you're just wasting data. So let's set this up. First thing we're going to do is we'll choose our tank B SOF. So there we go, and we can program that to the device, and all that does is does the exact same thing as the previous programmer did. Next thing we want to do is we want to add a clock. So if we go down to here, we press that box there, we get this dialog that comes up. Now what we want to choose is, in this, there's a bunch of things you can choose here. Most of the time we'll want to use SignalTap II pre-synthesis, and then we'll do a list. Now when you finally do a big MiSTer compilation, it will get so big that it will actually start to cause some problems, so you might have to do some other stuff. But here, typically pre-synthesis is what we want. So what we're going to do is we're going to choose on this one, I will choose what clock? We'll choose the PLL that we had, and we had a reference clock. Now the out clock was, if you remember, it was 18 megahertz. So that is our clock of our game effectively. The reference clock was the 50 megahertz, out clock was 18 megahertz. So let's choose that one. It's a bit lower. It'll certainly be fine. The sample depth we want to put to, let's put that to 2K. Everything else leave to auto. This can be very good in that it can trigger at certain times rather than straight away. We're going to have it triggering straight away, but you can have it triggering at a specific point if you want. Like everything in Quartus 2 and SignalTap, this is professional software. It gets very, very complex very quickly. So keep that there. Next thing we want to do is we want to add some things to look at. So make sure we're in the setup. The data tab and the setup tab look very similar. And if you're in the data tab trying to do set stuff, you're going to wonder what's going wrong. Make sure you're in the setup tab, and then you can double click. You get the same box coming up, and in the drop down again, make sure it's set to pre-synthesis and list, and it's going to find the same, effectively the same wires. So what we're going to look at is we're interested in looking at the reset, and we'll push that one over there. We're also interested in looking at the composite sync, which is VGA HS in our case, and we want to look at the blue, green and red VGA outputs. So we're going to put insert there and then close. So they've appeared in a nice box there. Now the point is our design has actually changed, because as I said, this interrogation is actually going to be on our FPGA. So this software said, well, hang on, your FPGA design has changed, so you have to recompile. So what we're going to do is press that button there, which is the same as the recompile button in Quartus 2. So we'll press that, and it says this particular file for SignalTap has been modified. Do we want to save it? Yes, we do. Where do we want to save it? Let it save in output files. No problem. Do we want to enable SignalTap? So here's where we can turn it on or turn it off. Of course we want to turn it on right now because we want to use it. Later on, if you're no longer interested in using SignalTap, you can turn it off again. So that's fine. This is going to compile, so I'll speed this up in the video. Okay, so we've compiled that, and then what we do is we go back to our SignalTap and we want to reprogram. So program them, obviously make sure that the MiSTer's turned on, it's connected via the USB as we did in episode 1. So reprogram device, it's going to send what we've just compiled down to it, and now it's say ready to acquire. If it doesn't say that, then something's gone wrong. We need to look at doing those steps again. But effectively it'll be one of a few reasons we're not using the correct SOF file or something like that. So now what we can do is we can do a single run analysis, which will get 2K's worth of data and then stop. So let's do that first. And that's what that looks like. So here, what have we got? we've got our reset button, and our reset button is naturally 1, and when we press it, it becomes 0. We've managed to capture nicely in that 2K a VBLANK, or a VSync in this case, sorry, even though it's it's an H sync in this case, I think, because we're looking at a composite sync. So yes, this is effectively one line of the screen, and then in that time we've got a blue, green, and red, and so we've got we're obviously seeing a pattern there of, you can see here we're having data there, and we can actually break those down to the exact, they're all the same, because obviously we've done that 6 times. Same with all of those. So that's good and it's useful, and you can zoom in and zoom out. But what is also maybe more useful is we can press auto run, and that will keep offloading that. And it's obviously not real time because it's much faster, but it is allowing you to see how that's changing. And sometimes you might want to see if something's particular is going on or going wrong. And what we can do is we can press the reset button, and we can see how that is stopping everything. Now, interestingly, I don't think I've got the reset button connected right, because it's not showing in the code that the reset button is going down to 0. So something up there, but honestly there's not much point in me troubleshooting that at this point. But you can certainly see how useful this is to see, is this what we're expecting to get? In this case we know it is, because we've also got a very good troubleshooting device, a CRT monitor that's plugged in showing exactly what it needs to. So we know everything's working just fine. But oftentimes that won't necessarily be the case, and we need to use this to interrogate different wires to see if you know, if we're getting what we expect to be getting. So after changing the green input horizontally to the 6 MHz signal, now we have discrete pixels on each line. You can't see it too well in the picture, but on the PVM it's clearly breaking up each pixel horizontally, not a solid line like is shown horizontally in the other colors. It's amazing to see how sensitive the CRT is to tiny time periods that dip to 0 on the 6 MHz waveform. So I'm happy that we got a picture showing in this episode. Join me next time and we'll be looking at what the color prompt chip is and how the chip works in the arcade display circuit. See you next time.